It's a pleasure and privilege to be here today. And since Emma kindly introduced me, I would like to start with familiarizing you with this beautiful piece of art, Weizstoss altarpiece. It's from the 15th century, the end of 15th century, and it's located in the main church in Krakow. Krakow at that time was a capital city. And the name of the church is St. Mary's Basilica. And the altarpiece is a pentaptych, 13 meters high, 11 meters wide. And the figures of the altarpiece are also quite substantial. They are 3 meters high. So I read that it's 12 feet around. And the diameter can be even up to 1 meter. So I guess it's 4 feet. Yeah, and our research group performed some microclimate analysis during 2014 and 2015. And here I'm showing you yearly data recorded by Marcin Strojecki. And some of you can recognize that data from the Harry E. workshop. And the yearly average of RH is 59%. We can treat this data as a representative microclimate of unheated historic interior from Central Europe. And since it is unheated, I would like to point out how cold it can be during the winter time. And we can see that in the first week of December of 2014, the temperature dropped to 8 Celsius degrees. And the relative humidity was about 50 to 60%. So we can imagine how uncomfortable it is to spend more time in Basilica during winter. Basically, it's like sitting in a large fridge. So to tackle that problem, many institutions, many priests, many churches, they install intermittent heating to provide some thermal comfort for their visitors. And it's not only for the religious ceremonies, but more and more places to, not need to rely on financial resources from government or whatever. They have a must and need to organize some commercial events like weddings, concerts. So more and more people, they have their requirements for thermal comfort. And on the data from Santa Maria Maddalena Church from Rocca Pietore, we can see how this heating what this heating causes. We see that the rise of temperature by 10 Celsius degrees caused dynamic drops of relative humidity of amplitude equal to 35 percentage points. And there exist some guidelines how the heating should be performed. So, in example, Danish and British recommendations, they say you should do it quickly for the short period of time, which is contradictory to what, for example, German Association of Restorers says, that the changes should be very slow, 3% daily. And in our research, we wanted to correlate those dynamic drops of relative humidity with the risk of fracture for the big, massive wooden objects like the sculptures of the altarpiece of Weizstoss. So the method of our research is finite element modeling. And the wood of our choice is lime wood, exactly like the sculptures of Weizstoss. And the other terms for that type of wood is linden or basswood, if it's more familiar for you. So the model is very simple. It's a half of the cross-section of the sculpture, because the longitudinal direction of wood can be here neglected with a fair approximation. And the model has the initial, it's called here crack depth, but actually it represents like the natural microflows in wood in its initial state. So it's not necessarily like a crack that you can see, but it can be a knot, some imperfections of wood that, it's not like a steel, homogeneous like a steel. And in our model, we look for the parameter called energy release rate, and actually whether it exceeds its critical level, G1C. So G can be considered as the rate at which energy is absorbed by the crack growth. And we obtained it through the integration over the certain area around the crack tip. And it depends on relative humidity, so in our model, on the time of the modeling. Here you can see more in detail where the mesh of the model is refined. It's exactly in the area where the integration of these parameters that can give you G is performed. So if the model delivers you the G value, the crucial point is to actually find the reference point, so G1C, to be able to tell when we are in the risky zone. And to do that, we performed mechanical testing, the so-called wedge splitting test, in the universal machine. We splitted limewood samples to obtain values of GF, and in the moment I will explain what is GF. And we did that for 3 different trunks of limewood, conditioned to 4 different levels of RH. And from the graph, you can see that there is a slight increase of GF with relative humidity. And then it got inverted in the very humid conditions. And also, the dispersion of the values is quite high in very humid conditions. But actually, we are talking about heating the church interior, so about very low relative humidity levels. So the area of our interest is on the right side of the graph, where we have quite, constant values. Since wood is not ideally elastic material, what we actually get from the mechanical testing is not G1C, but fracture energy, GF, which is somewhat larger than G1C. So to have a correction factor, we looked in the literature of the author of the experiment, and with a good approximation, if we multiply our GF values by 0.6, we obtain our value for our risk assessment. And we did that for the average for relative humidity of 35%. And our reference value will be 200 newtons per meter. So we have our model, we have a reference value, so let's move to considering some scenarios. What can happen in the basilica? So the first scenario that we looked at is exactly the situation like we saw in the Rocca Pietrone. So we are heating the church interior to the comfortable level of 11 Celsius degrees, so 64 Fahrenheit. And we assumed that it can cause a drop of relative humidity from 59% to 20%. And for the sake of modeling, it happens in the first second of the modeling. So on the x-axis, we have the duration of this low relative humidity condition. On the y-axis, we have various crack depths. And the dashed line, and the color indicates what is the value of G that we obtain in the modeling. The dashed line is our critical value. So clearly, in the first hours of modeling, there is area that no matter the crack depth, we are not in the risk zone. And the critical point is 12 hours, where there is a first crack depth that can cross this dashed line. So it was the first scenario was a very simple exercise in modeling. We had a stable T, we had 2 levels of relative humidity, but let's look at the actual impact of the real microclimate of Basilica on the sculpture of Weitstoss and how it is reflected in the G value. So I'm showing only the result for the crack depths recognized as critical. And we can see that, sorry, that is a little bit too fast, but let's look at the left side, that during the cold season, there is not a lot going on. Actually, we are close to the threshold, in the summer season. But what if our priest of St. Mary's Basilica wants to rise the temperature whenever it drops below the certain level? So we assumed we cut off some low temperature values and we replace them with a certain constant level. It's here. And this is how it changed our result. Here I show you clearly that in the cold season we raised our values substantially. And we recognized, due to this modeling, that 11 Celsius degrees is the maximum value to which the church interior can be heated without crossing this line of reference. And the third scenario that we considered is moving a sculpture to a conservation studio to perform some restorative works. And the concept of it is actually the same as the first scenario. So we have a step change, so immediate change of relative humidity. We lower it down, and we look how the G value changes in time and when it crosses our reference level. So for the certain crack depths, this curve has an inflection point, and that is why I read the maximum value. So this maximum value of G can happen here or here or here, and I read these maximum values for all of these crack depths that I considered and several amplitudes of array changed, and I plotted them here. And I'm showing you the curve for a 100 millimeter deep crack, which had the steepest curve of G1 max, considering different amplitudes of array change. And we can be quite surprised that actually our reference line is crossed with a change of 6% from the level of 59. And it brings a risk of fracture. So how is it that the natural microclimate of Basilica, yearly climate, was fine for the sculpture, and we saw the biggest drops of relative humidity than 6%? It is true, but we have to consider that if I would plot this change by 6% here, I would need to wait 9 months for the curve to reach the reference line. So it's all matter of time. And to summarize, I would like to go back to one of the first slides and check with whom are we consistent. And as we can see, the British and Danish recommendations can be supported with our research. And that was all. And as a young researcher, I had to thank all the projects that supported my research. And thank you for listening to my presentation.
No, okay. Well, we'll just shout. All right. Thank you so much for that. That's super. Let's open it up to questions, shall we? Oh, there's one at the back. Here we go. Please.
Sorry, hiding in the back. Can you talk a little bit more about what you assume for the relationship between the humidity and how much water was in the wood at equilibrium? Because that's where the stress actually comes from, I guess, right?
I hope that I got your question correctly. So you are right that those are the dynamic relative humidity changes. They bring the gradients of moisture content in the cross-section of sculpture. And that's what affects massive elements because they are never in equilibrium. You know, the relative humidity changes so fast that there are always certain areas with certain equilibrium moisture content, and this is what is reflected in the G value. And during mechanical testing, when we wanted to obtain, you know, the critical G value, we made sure that, you know, the whole specimen of wood has a constant equilibrium moisture content. So I'm not sure if it answers your question.
Yeah, well, it's just a question of what is the equilibrium water content and how do you figure out what that was to use in your simulations?
So
Can I help Magda a little bit? Or
of course. You can, but I mean in the sculpture there is no equilibrium moisture content because all of it happens so fast that, you know, there is a gradient. But Łukasz, you can explore
Magda repeated many times the climate in the museum, and she find out what is the zero stress level at which relative humidity at different depths in the. So in generally, it reflects the concept that object adapted to the long-term pattern of the fluctuation, but there is no constant level of the EMC in the sculpture.
Right, but when you drop the humidity, you're drying out the surface, putting in tension.
Yes.
So how much are you drying out the surface? There must be some.
So Magda, can you return to the relative humidity variation? And she said that it's 59% of average. This is the average level in the church.
By how much do you mean, like to what, in centimeters, or to which level of relative humidity?
So we can talk later. I'm going to get too bogged down, but the surface is at equilibrium with whatever your humidity is. So if you start out at high humidity and maybe there's 10% water in there, and you drop it and you go to 3% water, I'm just trying to figure out what your surface boundary condition is as a function of humidity and how you sorted out what to use for that.
Yes, would you like me to translate relative humidity to equilibrium moisture content? I think
Yes.
I did get you.
Yes.
So I cannot do it, you know, in my mind, probably like here from the stage. But we can look later at the graph because I would need, you know, a graph.
Okay.
Usually I operate with the relative humidity because this is what I insert in my parameter in the console. So that's what I'm more familiar with.
Okay, more questions? Michal? Do you want this?
Magda, thank you for your presentation. I'd like to ask about the importance of the depth or the size of the crack. And I see that all the results you are presenting are in function of this depth of the crack, and the G parameter depends on that. And I'd like to ask how the results depends on the size of the wooden element in which the crack is created. Is it like a parametric relation, or like?
Yeah, you are right. That's a very good question. And we performed that research. We are in the middle of performing that research. Mm-hmm. And yeah, apparently, when you increase the diameter, you increase your G values. That is true. And there is a certain diameter for which it doesn't matter. The dynamic changes didn't matter. But are you asking me if there is a ratio of crack depth and the diameter of sculpture, and it follows?
My understanding is that if you have a very massive element, very big one, then at some point it doesn't matter what is diameter because there is such a huge buffer there. But if you make the radius smaller and smaller, at some point this ratio between the depth of the crack and the diameter will influence. But you don't.
So far, I tested only 1 meter of diameter and 13 centimeters of diameter. So I didn't think that it's representative.
1 meter diameter of the trunk is quite massive, yes.
Yes, it's massive. And then my other research was on a 13 centimeters sculpture. So it's only 2 examples.
But is there a difference then between the 13 centimeters
I didn't
and 1
look
meter?
at it, actually, at the ratio. I need to look at it.
Okay, it's just very interesting. Thank you.
Okay, over here. Thank you.
Thank you very much for your interesting presentation. I have 2 questions. The first one, you consider just the behavior of the wood, but in case of the sculpture, you have the preparation color that cover completely, and that affects the diffusion in the wood. So a short time variation could be influenced also by the presence of the color. And I would like to know if you have considered these aspects. And the second question is, being a piece of solid wood that contains the beads, for sure during the seasoning of the wood, you have the opening of cracks, of big cracks, that broken the continuity of the structure. Have you simulated what could be the effect of the presence of, let me call it, an original big crack on the behavior of energy variation?
Mm-hmm. Yeah. Thanks for the question. So with the polychromy on the wooden sculpture, we made an initial assumption that since it would slow down the diffusion, we would like to consider the worst case scenario. We are focusing on dynamic changes. So the polychromy would slow everything down. So the sculpture would have a little more time to equilibrate everything what's happened. So that's what we decided. We go for the worst case scenario. And when we are asking if we considered the big crack, did you mean modeling? Yeah. So if you would look at the crack depths, let's go back. So actually, if the sculpture has 1 meter of diameter, we covered with this crack depths almost, everything up to the radius of the sculpture. So the maximum is 45 centimeters, the maximum crack depth that we considered. And I couldn't go further because, you have a singularity. You are in the middle of the sculpture. So yeah, I think I can say that we covered that scenario in our modeling. Is it the answer you were looking for?
All right. We really probably don't have time for another question, but thank you so much. That was fabulous. Round of applause, please.
Thank you so much.